Hi everyone, myself Valli Rani, Assistant Professor in Physics in Ramchandra College of Engineering. In this video, we will discuss about Raleigh's criteria for resolving power and resolving power of grating. Before going to discuss about this topic, let's talk about objectives and outcomes of diffraction of light. The objective of diffraction of light is learning about theories of light, diffraction grating, and resolving power of optical instruments. Now let's see outcome. On successful completion of this diffraction video, the student should able to gain knowledge on various theories of light. He acquired skills to identify and apply formulas of optics and wave physics. He able to understand the applications of diffraction, and the student should able to understand the resolving power of different optical instruments. So these are the objectives and outcomes of diffraction of light. Now here first we discuss about Raleigh's criterion for resolving power. Here what is meant by resolving power? Let's see, when two objects are very nearer to each other, they may appear as one, and it may be impossible for the eye to see them separately. If we want to see as separate objects, we make use of optical instruments such as telescope, microscope, prisms, gratings, etc. The separation of such objects is termed as resolution. The separation of such objects, close objects, is termed as resolution, and the ability of optical instrument to form distinctly separate images of two closer objects is called resolving power. That is, the resolving power of an optical instrument is defined as the ability to just resolve the images of two close point sources or small objects. The resolving power is the ability of instrument to measure the angular separation of two images that are close to each other. In order to obtain definite measure of the resolving power of instrument, Rayleigh suggested a limit of resolution called Raleigh's criteria. According to Rayleigh, two images of closely separate objects, either spectral lines or point sources, said to just resolve if in diffraction patterns the central maxima of the first image coincides with the first minima of second image or vice versa. That is, the two images or two spectral lines of equal intensity should be regarded as separate, that is just resolved, if the central maxima of the diffraction pattern due to first spectral line or image coincides with the first minima of second spectral line and vice versa. This is known as Raleigh's criterion for resolving power, and it can be applied to calculate the resolving power of telescope, microscope, grating, prism, etc. To express the resolving power of an optical instrument as a numerical value. In order to understand the Raleigh's criteria, let us take a diffraction pattern of two spectral lines having wavelengths lambda and lambda plus d lambda. And the wavelength difference is d lambda, and the difference in angle of diffraction is d theta. Now, to understand Raleigh's criteria, let us take two spectral lines of wavelength lambda and lambda plus d lambda, and its wavelength difference is d lambda, and difference of angle of diffraction is d theta. So, to understand the Raleigh's criteria, here we observe three cases. Now let us see the first case. In this case, the difference in wavelengths of two spectral lines is small d lambda is small. In this case, we will observe the resultant intensity distribution curves for two spectral lines lambda and lambda plus d lambda. Here we observe the central maxima in the diffraction pattern of lambda coincides with the first minima in the diffraction pattern of lambda plus d lambda. Once again, here the central maxima of diffraction pattern of wavelength lambda coincides with the first minima. This is the first minima in the diffraction pattern of wavelength lambda plus d lambda and vice versa. According to Raleigh's criteria of resolution, the two spectral lines are said to be resolved, means seen as separate. The two spectral lines of wavelength lambda plus d lambda satisfies this condition. And the resultant pattern, the resultant intensity pattern has a dip at the middle of the two spectral lines. So, here these two spectral lines satisfies the Raleigh's criteria. Hence, these two spectral lines are seen as separate like this. In this case, the two spectral lines are seen as separate. Next, we will see the second case. If d lambda, so d lambda is the wavelength difference of the two spectral lines is very large. So in this case, we will observe the diffraction patterns of two spectral lines lambda plus d lambda and lambda like this. Here, the two intensity distribution curves are well resolving condition and the resultant images are in well resolved condition. Here, the two images are seen as separate in this case also. And we will see the third case. In this case, if d lambda is too small, here the wavelength difference between the two spectral lines is too small. In this case, the resultant intensity distribution, there is no dip. That is, here the central maxima in the diffraction of wavelength lambda overlaps with the central maxima in the diffraction pattern of wavelength lambda plus d lambda. Here, the central maximas of two spectral lines are overlapping with each other, hence there is no dip at the middle of the resultant intensity distribution curve. Here, the two spectral lines cannot seen as separate. The two spectral lines are not resolving condition in this case. Therefore, from the above discussion, it is clear that the two spectral lines are resolved only when two wavelengths satisfies Raleigh's criterion of resolution. Here, the two spectral lines of wavelength satisfies Raleigh's criterion of resolution. So, Raleigh's criterion is the central maxima in the diffraction of lambda coincides with the central first minima in the diffraction pattern lambda plus d lambda. So, this satisfies the this condition. Then the two spectral lines are just seen as separate according to Raleigh's criteria. So this is about Raleigh's criterion for resolving power. Now we will discuss about resolving power of plane transmission grating. Here the resolving power of grating, it is an important property of diffraction grating. The diffraction grating is its ability to separate adjacent spectral lines of two nearby wavelengths lambda and lambda plus d lambda. That is, the resolving power of plane transmission grating is its ability to show two neighboring lines in a spectrum as separate. That is the resolving power of a grating. So, ability of an optical instrument. The resolving power of grating is its ability to show two neighboring lines in a spectrum as separate. Here, the resolving power of grating may also be defined as the ratio of wavelength of any spectral line. Wavelength of any spectral line lambda to its difference of wavelengths of this line and neighboring line, such that the two spectral lines can be just seen as separate. Here, the resolving power of grating is represented by lambda by d lambda. It is the ratio between wavelength of any spectral line to its wavelength difference of this line and neighboring line. So, this line and neighboring line, its difference is d lambda. So, ratio of this one gives the resolving power of a grating. Resolving power of grating. Now, we will derive the expression for resolving power of grating. For this, let us consider two spectral lines S1 and S2 of wavelengths lambda and lambda plus d lambda or diffracted at an angles theta and d theta plus d theta. The two spectral lines S1 and S2 of wavelengths lambda and lambda plus d lambda at a diffraction angles theta and theta plus d theta. According to Rayleigh's criteria, these two spectral lines are just resolved if the central maxima of S2 coincides with the first minima of S1 and vice versa. So, in this case, the two spectral lines are seen as separate according to Rayleigh's criteria. Now, we will see the spectral lines S1 in the direction of theta plus d theta. The spectral line S1 in the direction theta plus d theta, we will get first minima of spectral line S1. So, first minima of S1, the condition for first minima, mth minima is n into e plus d sine theta plus d theta is equal to plus or minus m lambda. This is the condition for minima, mth minima of a spectral line of wavelength lambda in the direction theta plus d theta. Here capital N represents there is n number of equidistant parallel slits on the diffraction grating per unit width. Okay. But here this minimum intensity which is adjacent to principal maxima of lambda plus d lambda, this is only obtained by substituting the value of m by n into capital N plus 1. Then this m value substitute in the equation 1, we will get the expression, final expression n into e plus d sine theta plus d theta is equal to small n into capital N plus 1 into lambda. So, this condition gives the minimum intensity of the spectral line of wavelength lambda in the direction theta plus d theta. At the same direction, we will get central maxima of principal maxima of the spectral line of wavelength lambda plus d lambda. Now, we will see the condition for principal maxima of lambda plus d lambda is for spectral line S2 in the direction theta plus d theta. So, in the direction theta plus d theta, S2 spectral line will having central maxima or principal maxima. That condition is e plus d sine theta plus d theta is equal to n into lambda plus d lambda. So, here is this condition represents the principal maxima of spectral line of wavelength lambda plus d lambda in the direction theta plus d theta. Now, we will multiply it with the capital N by equation 3. We will get capital N into e plus d sine theta plus d theta is equal to capital N into small n into lambda plus d lambda. Now, comparing the equations 2 and 3, then left hand side portions are cancelled with each other and remaining portions will be capital N into small n lambda plus d lambda is equal to capital N small n plus 1 into lambda. Now, we will simplify this expression. We will get capital N into small n into d lambda is equal to lambda. Now, d lambda will be shifted to this side. We will get lambda by d lambda is equal to capital N into small n. Here lambda by d lambda gives the resolving power of a grating. From the definition, the ratio between wavelength of any spectral line to wavelength difference of this line and neighboring line, that is d lambda, which gives the resolving power of grating. The resolving power of grating lambda by d lambda is equal to capital N into small n. Here capital N represents the number of lines or number of grating elements per unit width of the diffraction grating, and capital N represents order of the maxima. Here the resolving power of grating is always directly proportional to order of the maxima small n and number of lines or grating elements per unit width of the diffraction grating. Here as increasing small n, then the resolving power of grating is also increases if n kept constant, capital N kept constant. As capital N increases, then resolving power of grating is also increases if small n kept constant. Finally, the resolving power of grating is directly proportional to number of grating elements per unit width of the diffraction or number of lines per unit width of the diffraction and order of maxima. So this is about the resolving power of grating. Now we will see some of the important questions about this topic. State and explain Rayleigh's criterion for a limit of resolution. State and explain Rayleigh's criterion for the limit of resolution, or write notes on Rayleigh's criterion. For this, we give the answer. According to Rayleigh, two images or two spectral lines of equal intensity should be regarded as separate, that is just resolved, if the central maximum of diffraction pattern due to the first spectral line or image coincides with the first minima of spectral line and vice versa. This is known as Rayleigh's criterion for the limit of resolution. Now let's see. Define resolving power of grating and derive the expression for resolving power of grating based on Rayleigh's criteria. For this, the resolving power of grating. The resolving power of grating is defined as the ratio between wavelength of any spectral line to the wavelength difference of this line and neighboring line, that is lambda by d lambda gives the resolving power of grating, and this resolving power of grating is always directly proportional to number of grating elements per unit width of the diffraction grating and order of maxima. These are the important questions for this topic, and this is the complete detailed explanation about Rayleigh's criterion for resolving power and resolving power of grating. Thank you.